Mid-February 1943, Sidi Bou Zid, Tunisia, the captured M4A1 Sherman tank came to a halt in the desert sand, its American star still faintly visible beneath a quickly painted German cross. Officers from Heavy Panzer Battalion 501 gathered around the prize, notebooks already open. This single American tank, captured intact and fully operational during the fighting at Sidi Bou Zid, would spark a crisis of confidence among German engineers that echoed through their tank development programs for the rest of the war. The mathematics of armored warfare were about to change, not through thicker armor or greater firepower, but through something German designers had never truly prioritized: automotive reliability that simply refused to fail. The tank carried the name War Daddy II painted on its hull. Serial number USA 3067641, produced by Lima Locomotive Works, assigned to Company G of the 1st Armored Regiment, 1st Armored Division. Personnel from a German reconnaissance unit drove this Sherman 350 kilometers across the harsh North African landscape to the port of Sfax, a journey lasting 4.5 days. Every kilometer revealed something that contradicted German assumptions about American industry. The engine never overheated, the transmission never broke down, the final drives maintained steady performance. German tank crews, accustomed to frequent mechanical stops even on short movements, watched with growing unease as this enemy vehicle simply continued operating without complaint through terrain and conditions that would have disabled their own machines. At the port, War Daddy II was loaded onto a cargo ship bound for Germany. The Army Weapons Office had issued clear instructions. This tank must arrive at the testing facility in Kummersdorf intact and operational. German intelligence had previously received fragmentary reports about American tank production. But seeing the physical vehicle made those numbers real in a way statistics never could. The Sherman represented mass production on a scale Germany could not match, built with automotive engineering principles the Germans had not mastered. As the ship steamed north across the Mediterranean, Wehrmacht engineers prepared testing protocols that would reveal truths they had long been reluctant to face about both their own limitations and American industrial capability. Spring 1943, Kummersdorf Proving Ground, Brandenburg, Germany. War Daddy II rolled down from the transport railcar carrying the designation Zugkraft 259 and German military license plate WH058941. Test engineers had already marked armor thickness measurements and angles across every surface of the tank, covering it with precise technical notations for their evaluation program. The German Army Proving Ground at Kummersdorf, located roughly 25 kilometers south of Berlin, served as the primary testing center for both German and captured Allied equipment. Here, methodical engineers measured, tested, and analyzed everything from track tension to transmission efficiency, recording their findings in exhaustive technical reports. The Sherman was about to undergo the most comprehensive automotive examination German engineering could devise. German test engineers began their inspection with teams of specialists drawn from multiple technical branches. They photographed every component from dozens of angles, measured every clearance with precision instruments, and documented construction techniques that appeared astonishingly simple compared to German manufacturing methods. The transmission immediately drew attention from powertrain specialists. Where German tanks relied on straight-cut gears, requiring extremely precise tolerances and frequent maintenance, the Sherman used herringbone gears, which distributed mechanical stress across multiple gear teeth simultaneously. This design, standard in American automotive production since the 1930s, provided exceptional durability while requiring far less manufacturing precision. German engineers had previously considered herringbone gears too difficult to mass-produce with their existing industrial capabilities and workforce training. The Americans, however, had already been producing them by the thousands. The testing began with basic automotive trials designed to push every mechanical system under controlled conditions. Engineers drove War Daddy II through obstacle courses intended to simulate battlefield terrain, measuring fuel consumption, monitoring engine temperatures, and recording transmission behavior under different loads and surface conditions. After each trial, they dismantled components to inspect wear patterns, searching for signs of stress, lubrication failure, or design weakness. The results contradicted nearly everything German armored doctrine had assumed about the trade-offs between performance and reliability. The Sherman performed adequately in every category, but it excelled in the one area German tanks consistently struggled with: operational endurance without mechanical intervention. The powertrain analysis revealed deeper design philosophy differences between American and German engineering. The Sherman transmission provided 5 forward gears and 1 reverse, with synchronization in gears 2 through 5, eliminating the need for double clutching during normal driving. This allowed the tank to be operated almost like a civilian automobile, requiring minimal specialized training for drivers. German tanks, by contrast, demanded far greater mechanical skill from their crews, making them more complex to operate and maintain under battlefield conditions. German tank crews, by contrast, spent long periods mastering complicated double-clutching techniques and careful throttle control in order to prevent damage to their transmissions. The Sherman's design assumed that ordinary soldiers with only basic automotive knowledge would operate the vehicle, while German tanks were built with the expectation that highly trained specialists would always be available. The Continental R975 radial engine installed in this Sherman displayed remarkable tolerance for changing operating conditions. Engineers observed that the engine delivered stable performance across temperature ranges that would have caused many German engines to overheat or lose power. The cooling system, although simple in construction, proved extremely effective. The air filtration system coped with desert sand without the constant clogging that had plagued German vehicles in North Africa. Every major system reflected a design philosophy focused on practical reliability rather than theoretical perfection. June 6 and 7, 1943, Hillersleben Artillery Range. Reich Minister Albert Speer arrived to oversee a major armaments conference attended by leaders of the German defense industry and senior Wehrmacht officers. The demonstration program included hill climbing trials comparing German tanks with captured Allied vehicles. War Daddy 2 stood beside the newest German machines, including a Panther IV, fresh from the production line, and a Ferdinand tank destroyer, representing Germany's most advanced armored fighting vehicle technology. Speer, responsible for armaments production and personally accountable to Adolf Hitler, needed a clear understanding of what American industry was producing and how German designs compared with enemy equipment. The demonstration would provide answers that neither Speer nor the German tank designers wanted to hear. The Sherman climbed the testing slope smoothly. Its manual transmission, with 5 forward gears synchronized from 2nd through 5th, shifted without hesitation. The engine maintained steady power during the entire climb. The driver handled the vehicle confidently, demonstrating the ease of operation that would become a defining characteristic of the Sherman. The Panther followed. Its more powerful 700 horsepower Maybach HL230 engine allowed it to match the Sherman's performance, but only barely, and with far greater difficulty. The Ferdinand, enormously heavy at 65 tons and technically sophisticated with its electric transmission system, stalled halfway up the slope. Speer watched as recovery crews attempted to restart the vehicle, an embarrassing failure witnessed by dozens of senior officers and industrial leaders. Years later in his memoirs, Speer described the Sherman's capabilities that he personally observed during an inspection tour of Italy in October 1944. He noted that reports regarding the Sherman's cross-country mobility had been extremely favorable, with the tank climbing mountainous terrain that German tank experts considered inaccessible to armored vehicles. Speer attributed this to the Sherman's strong engine relative to its weight, which provided cross-country mobility on level ground clearly superior to German tanks. The 26th Panzer Division had specifically reported this advantage in operational reports. Observations coming from Germany's armaments minister carried significant influence within Wehrmacht leadership circles. A public summary appeared in the newspaper Das Reich on June 27, 1943. The article described the Sherman as one of the notable achievements of North American engineering laboratories and referred to it as a highly commendable product of the North American steel industry. The article emphasized that the first striking characteristic was its serial production and the fulfillment of the demanding requirements typical of the North American automobile industry. It also mentioned the Euro-stabilized gun, describing it as the first attempt of its kind to be implemented anywhere, acknowledging American innovation in this area. These public statements were carefully phrased to avoid appearing defeatist for propaganda purposes. Yet behind the official language lay growing concern among German engineering departments. American tanks were not merely adequate. They were fundamentally better engineered for sustained field operations. Back at Kummersdorf, systematic testing continued through the summer and into the autumn of 1943. Engineers measured the Sherman's operational range during extended trials that pushed the vehicle close to its mechanical limits. They documented operational distances exceeding 2,000 kilometers before major maintenance became necessary, roughly 4 times the endurance early model Panthers could achieve under real combat conditions. They measured transmission efficiency that surpassed any German tank design, with drivetrain power losses significantly lower than comparable German systems. They studied the synchronized manual transmission that made gear changes smooth and simple, eliminating the need for double clutching or precise engine rev matching that German gearboxes demanded. The final drive system revealed yet another design advantage that challenged long-held German engineering assumptions. The Panther's final drive system had been inherited from the Tiger tank, a configuration that proved vulnerable under heavy loads. It used straight-cut gears housed in assemblies that struggled to handle the stresses created by a 45-ton vehicle. German mechanics in North Africa and on the Eastern Front had repeatedly reported final drive failures that forced Panthers to be abandoned after relatively short distances, sometimes after less than 100 kilometers of movement. The Sherman's final drives, constructed using the same herringbone gear principles as its transmission, almost never failed, even under prolonged combat conditions that would have destroyed similar German components. Restoration projects many decades later discovered Sherman final drives that required no mechanical restoration after long periods of storage, demonstrating design margins that exceeded immediate requirements by a considerable margin. By late 1943, the Kummersdorf Proving Ground had gathered enough data to produce detailed internal reports circulated among Wehrmacht technical departments. These documents, intended for senior officers and officials from the Armaments Ministry, presented a sobering comparison of capabilities. The Sherman revealed a level of American automotive engineering maturity that Germany simply did not possess, despite its strong theoretical knowledge and scientific expertise. Mass production techniques allowed manufacturing tolerances that German precision engineers would have considered imprecise. Yet these designs resulted in vehicles that proved more reliable and easier to maintain in real battlefield conditions. Interchangeable parts allowed field repairs to be performed with basic tools and minimal specialized training. German vehicles, by contrast, often required factory-level precision and specialized equipment for repairs. The entire American design philosophy focused on keeping vehicles operational, rather than achieving theoretical performance figures that looked impressive on paper but were difficult to sustain in combat. Internal German engineering assessments also documented deeper industrial advantages enjoyed by the United States. American automotive engineering reflected decades of civilian industry experience that Germany had never developed on a comparable scale. Before the war, automobile ownership in the United States had become widespread, with cars common among ordinary citizens across nearly every economic class. Germany, however, had far less civilian automotive experience. Automobiles remained largely luxury items available primarily to wealthy individuals and party elites. The Volkswagen program, promised to German workers in 1934, had delivered fewer than 1,000 civilian vehicles by 1939. This massive difference in automotive industry maturity translated directly into contrasting tank design philosophies. American engineers built tanks that mechanics with ordinary civilian automotive training could maintain using skills they already possessed. German engineers built tanks that required specialist training and continuous attention from technicians with years of military technical education. By late 1943 and early 1944, comparisons in reliability between German tanks and the Sherman had become impossible to ignore as operational reports accumulated. Panther tanks required strict operational limitations to prevent mechanical breakdowns that could leave them immobilized. Drivers received clear instructions not to shift gears frequently because excessive gear changes could damage the transmission. Third gear failed frequently enough that field manuals warned drivers to avoid using it except when absolutely necessary. Panthers also could not turn while reversing, because doing so could destroy the transmission. Pivot turns were only possible when ground resistance remained equal on both tracks, which severely limited tactical maneuverability. Foreign objects entering the running gear could jam the drive sprocket, often requiring hours of maintenance to clear. These mechanical weaknesses existed despite Panthers being manufactured in dedicated tank factories by skilled workers using the best materials available in Germany. The Sherman, by contrast, had been designed by automotive engineers at General Motors, Ford, and Chrysler, applying mass production techniques developed through decades of civilian automobile manufacturing. The tank incorporated commercial automotive components wherever possible, taking advantage of established supply chains and existing manufacturing expertise. The transmission was produced by multiple companies, including Caterpillar Tractor, Buick, and Ford Motor Company, all manufacturing to identical specifications with completely interchangeable parts that could be installed freely without modification. This level of standardization, routine within the American automotive industry, remained largely theoretical in German tank production. German manufacturers often introduced small design variations that prevented true interchangeability of parts. Additional captured Shermans arrived at Kummersdorf during 1943 and 1944, including vehicles captured from British forces in Italy and Soviet units on the Eastern Front. Each tank underwent similar testing procedures, gradually building a detailed database of American armored vehicle performance across multiple variants and production periods. The British had modified some Shermans by installing their powerful 17-pounder anti-tank gun, creating the Firefly variant that addressed the Sherman's primary weakness in firepower. German engineers studied these modified tanks with particular interest. They noted how the Sherman's large turret ring allowed the installation of a significantly larger gun with relatively minor modifications. The Firefly demonstrated growth potential built into the original Sherman design, something German engineers had not fully considered when designing their own vehicles. The Panther, rushed into production primarily to counter the Soviet T-34, lacked the internal space and structural flexibility for major armament upgrades without a complete redesign of both turret and vehicle. As testing continued, the automotive evaluation program expanded to include reliability trials specifically designed to simulate combat conditions. Engineers drove Shermans through hundreds of kilometers of cross-country movement, carefully recording every mechanical incident, maintenance requirement, and component failure. They compared these results with field reports from Panther and Tiger units operating on the Eastern Front and in Italy. The numbers revealed a clear and unmistakable story about reliability. Panther operational readiness averaged below 40% through most of 1943, with some units reporting catastrophic levels as low as 20 to 25%. Individual Panther battalions documented periods when fewer than 1 out of 5 tanks was actually capable of combat operations. Sherman tanks, by comparison, maintained significantly higher operational availability across all theaters of war. Detailed German field reports described Panther reliability problems with brutal clarity. In July 1943, during Operation Citadel at Kursk, Panthers achieved only 16% operational readiness, with mechanical failures disabling more tanks than enemy action. By December 1943, readiness had improved to only 37%. Reports from February 1944 still showed 37% operational availability. April 1944 reached 50%. By May 1944, readiness finally climbed to 78%. These figures represented the percentage of Panthers actually capable of combat on any given day. The remainder were broken down, awaiting spare parts, or undergoing repair work. Although the numbers improved gradually as design flaws were corrected, even the best Panther readiness levels never matched the reliability that Sherman tanks achieved from the beginning of production. By December 1943, the pattern had become impossible to ignore for any engineer reviewing the data. The engine lifespan of the Sherman diesel variant exceeded 3,000 kilometers when properly maintained. The Panther engine lifespan rarely reached 1,000 kilometers, even after improvements corrected the most severe early failures. German reports from March 1944 noted that improved Panther engines achieved a service life of 700 to 1,000 kilometers, which was presented as a major technical success. In reality, this improvement only brought Panther engines to roughly one-third of the durability of Sherman diesel engines. Sherman transmissions required minimal maintenance between overhauls, and their synchronized gears reduced the likelihood of driver mistakes damaging the system. Panther transmissions required constant attention and frequent repair. Third-gear failures were so common that drivers learned to shift directly from second to fourth gear to avoid using the problematic gear ratio. Sherman final drives functioned reliably under conditions that routinely destroyed Panther final drives within 100 to 200 kilometers of operation. Field reports from German units using captured Shermans confirmed the results of the Kummersdorf testing program through real operational experience. German mechanized units, increasingly desperate for reliable vehicles as their own armored forces deteriorated, eagerly used any captured American tanks they could obtain intact. Unlike captured Soviet T-34 tanks, which Germans often modified before service, Shermans entered German service without modification. They required no redesign because they functioned correctly exactly as they had been built, with no major design flaws requiring correction. German tank crews who had endured repeated mechanical failures in their own vehicles frequently described the Shermans' reliability in letters and official reports. Reports from panzer regiments noted that Sherman crews could focus on tactical maneuver and combat performance, while Panther and Tiger crews constantly worried about whether their vehicles would reach the battlefield without mechanical failure or complete a mission before a breakdown immobilized them. In January 1945, the 10th SS Panzer Division captured 12 M4A3 Shermans at Hatten-Rittershofen during Operation Nordwind. These tanks belonged to the American 43rd Tank Battalion and were captured intact when their crews abandoned them during the German assault. The 12 Shermans were organized into the 13th Company of the 10th SS Panzer Regiment, where they served in combat operations for the remainder of the war. These vehicles were used primarily for reconnaissance missions and mobile reserve roles, tasks that required sustained movement and dependable mechanical performance without frequent maintenance stops. German commanders recognized what testing at Kummersdorf had already proven years earlier. American tanks could be trusted to function when required. In the final months of the war, this dependability mattered more than armor thickness or gun power. A Sherman that reached the battlefield with a working gun was far more valuable than a Panther with superior firepower that had broken down 20 kilometers behind the front lines. January 1944 brought expanded testing programs as Wehrmacht forces retreated across several fronts and additional captured equipment arrived at Kummersdorf. Engineers examined the M4A1 Sherman equipped with the Continental R975 radial engine, documenting its characteristics and comparing it with other Sherman variants. They tested the M4A2, powered by twin General Motors 6046 diesel engines, noting its improved fuel efficiency and different operating characteristics. They also evaluated the M4A3, equipped with the Ford GAA V8 gasoline engine, which American crews considered the best power plant used in the Sherman series. Every variant demonstrated the same essential characteristic: exceptional automotive reliability, derived from sound engineering principles and well-established manufacturing practices. The consistency across different Sherman variants impressed German engineers, who were accustomed to significant quality variations between different production batches of their own armored vehicles. Different manufacturers producing nominally identical vehicles often created noticeable differences in German equipment. The diesel-powered M4A2 Sherman particularly impressed engineers who examined it at Kummersdorf. Soviet forces had received 4,102 of these tanks through Lend-Lease, and many later fell into German hands during withdrawals on the Eastern Front. The twin GM 6046 diesel engine delivered performance comparable to other Sherman variants while consuming significantly less fuel than gasoline engines, an important advantage as German fuel supplies continued to shrink. German engineers had experimented with diesel tank engines earlier in the war but abandoned the effort because of manufacturing difficulties and the complexity of diesel fuel injection systems. American industry, however, produced diesel Shermans alongside gasoline versions without disrupting production schedules. This demonstrated a level of manufacturing flexibility and technological organization that German industry never achieved during wartime. March 1944 brought official reports from General Heinz Guderian, Inspector General of Panzer Troops. In his communications, he noted that improvements to Panther reliability had finally achieved what he described as acceptable standards by early 1944. Engine life had increased to 700 to 1,000 kilometers, and final drive failures had been largely reduced through design changes and improved manufacturing techniques. German military communications presented these improvements as a major success. In reality, the improved Panther reliability merely reached a level the Sherman had already achieved from the beginning of production in 1942. The German army was celebrating the achievement of standards that American tanks had exceeded from the start, an uncomfortable indication of how far German armored development had fallen behind. The comparison became even more painful as German tank production struggled with worsening shortages of resources and the effects of Allied strategic bombing. Allied air attacks increasingly targeted critical bottlenecks in the Panther and Tiger production chain. The Maybach engine plant in Friedrichshafen suffered heavy damage during a Royal Air Force Bomber Command raid on the night of April 27 to 28, 1944. The raid involved 322 aircraft and is described in Imperial War Museum archives as the most damaging attack on German tank production during the entire war. The bombing also destroyed the nearby ZF gearbox factory, which produced transmissions for German armored vehicles. Production of tank engines and transmissions stopped completely for 6 months. When manufacturing finally resumed in November 1944, quality control had deteriorated dramatically. Slave labor, increasingly used in German factories as skilled workers were drafted into the military, introduced widespread sabotage. Cigarette filters were stuffed into oil passages. Gaskets were deliberately installed incorrectly. Components were assembled without proper clearances. None of these problems affected Sherman production. Shermans were manufactured in American factories located safely far from any combat zone and staffed by workers earning stable wages under far better conditions. The fundamental difference between American and German tank production did not lie in engineering knowledge, but in industrial capability and design philosophy. German engineers understood automotive engineering principles just as well as their American counterparts. They possessed extensive theoretical knowledge and strong scientific expertise. However, they did not consistently apply those principles to tank design. Instead, German designers prioritized characteristics that produced impressive specifications but often resulted in poor reliability under battlefield conditions. The Panther's powerful 75mm KWK-42 gun and thick frontal armor came at the cost of an overstressed powertrain that struggled to support the vehicle's 45-ton weight. The Tiger tank's formidable capabilities required complex maintenance procedures and frequent repairs performed by highly trained specialists. These compromises might have been acceptable if German industry had been capable of producing enough vehicles and spare parts to support them. It was not, especially as Allied bombing intensified and shortages of raw materials worsened. American engineers, trained in mass production methods through decades of civilian automotive experience, designed tanks that could be produced in tens of thousands and maintained by mechanics with basic training using skills learned in civilian life. The Sherman powertrain incorporated components already proven in commercial service, with design principles borrowed directly from automobile and truck manufacturing. The electrical system even included a backup generator capable of powering turret rotation when the main engine stopped, a feature that seemed like unnecessary luxury to German designers but proved extremely valuable during combat. German tank crews could only imagine such conveniences, especially those who had experienced turret mechanisms failing when engines stalled on steep slopes. These practical features rarely appeared in German technical specifications because German designers did not consider them priorities compared with armor thickness and gun power. By spring 1944, Wehrmacht units on every front reported increasing mechanical problems as manufacturing quality declined and spare parts became harder to obtain. Panther tanks required rail transport for movements longer than 100 kilometers because their mechanical systems could not reliably sustain long-distance road travel. The Panther's final drives could not survive prolonged road marches. Field commands issued strict orders limiting Panther movements so that vehicles would not be lost to mechanical failure before even reaching the battlefield. The Burge Panther recovery vehicle, built on the Panther chassis and intended to recover disabled Panthers, suffered from the same reliability problems as the tank it was supposed to rescue. German commanders increasingly faced the grim reality that mechanical failures destroyed more tanks than enemy action. Some units reported that as many as 70% of their tank losses resulted from breakdowns rather than combat damage. Meanwhile, Sherman production continued at a pace that German industry could never match. American factories built 49,324 Sherman tanks during the war, more than the total German production of tanks of all types combined. British Commonwealth forces received thousands through Lend-Lease. The Soviet Union received more than 4,000 diesel-powered variants. Chinese forces operating in Burma used Shermans effectively against Japanese armor that was technologically inferior to both American and German designs. Every theater in which Shermans served confirmed what the testing at Kummersdorf had already demonstrated. When properly maintained, Shermans continued operating under conditions that would disable or destroy German tanks. German tank crews who captured and used Shermans consistently praised their automotive reliability in letters, reports, and later interviews. Reports from the Eastern Front noted that German mechanics found even the complicated Chrysler A57 multibank engine, with its 5 separate engine blocks, easier to diagnose and repair than German tank engines that required specialized equipment and expert knowledge. The Ford GA V8, highly praised by Allied crews for its reliability and power, seemed exceptionally dependable to German mechanics accustomed to Maybach engines, which required constant adjustment of valve clearances, ignition timing, and carburetor settings. The General Motors twin-diesel engine, which the U.S. Army had rejected for its own use and instead assigned to Lend-Lease production, still exceeded the performance and durability of any diesel engine German industry had produced for armored vehicles. Another advantage of the Sherman came from its generous design margins. The transmission and final drive components originally designed for the 30-ton M4 Sherman with a 400-horsepower engine required no major modification when installed in the much heavier 42-ton M4A3E2 Jumbo assault tank, which carried substantially thicker armor. The same components also successfully transmitted 650 horsepower from experimental engines without requiring reinforcement or structural redesign. German engineers often considered such overengineering wasteful, believing that extra capacity increased cost and consumed scarce materials without immediate benefit. American engineers, however, understood that design margins provided growth potential for future upgrades and ensured long-term battlefield reliability, making the additional investment worthwhile over the vehicle's service life. By summer 1944, German tank commanders confronting the Allied invasion of Normandy recognized that their technical disadvantages extended far beyond the performance of individual tanks. American artillery superiority, overwhelming close-air support, and immense logistical capacity combined to overpower German forces regardless of armor thickness or gun caliber. But the Sherman's reliability created an additional and decisive advantage. American armored units could sustain continuous operations in ways that German panzer divisions simply could not. American tank battalions could launch attacks, fight extended engagements, pursue retreating forces, and immediately prepare for the next operation without lengthy maintenance delays. German panzer divisions had to carefully conserve their limited operational vehicles, knowing that every movement reduced the remaining lifespan of critical components and increased the risk of mechanical failure. Operational availability ultimately determined which army could maintain constant offensive pressure, and which army was forced to ration its remaining combat power. German use of captured Shermans in combat operations provided final confirmation of American automotive superiority. The 150th Panzer Brigade, formed specifically for infiltration missions during the Battle of the Bulge in December 1944, attempted to obtain captured American vehicles to disguise its forces. German planners wanted Sherman tanks in particular because of their reputation for mechanical reliability. However, the brigade managed to obtain only 2 Shermans, and only one was in condition to operate. Even that vehicle never entered combat. Massive traffic congestion during the operation prevented the infiltration plan from succeeding. In a mission that required vehicles capable of operating behind enemy lines without mechanical support, only American equipment offered a realistic chance of success. German tanks, even when fully operational, could not guarantee the same level of reliability under such demanding conditions. Such missions demanded sustained mechanical performance that German tanks could rarely guarantee. January 23, 1945 brought the final official acknowledgement of Germany's automotive failure. A meeting of the Panzer Commission produced a report documenting catastrophic final drive failures across nearly all German armored vehicles. The report's findings were devastating. Before the 1945 Eastern Offensive, the German army recorded 500 defective final drives in Panzer IV tanks, 370 in Panthers, and approximately 100 in Tigers. In addition, roughly 200 failures had been reported in the Hetzer tank destroyer, which was based on the Czech 38-ton chassis. General Wolfgang Thomail, General Lieutenant and Chief of Staff to the Inspector General of Panzer Troops serving under Heinz Guderian, described the operational consequences in stark language. Under such circumstances, he explained, orderly deployment of armored units was simply impossible. Tank crews lost confidence in their vehicles. In some cases, entire tanks were abandoned because of final drive problems, as crews feared becoming stranded and captured. German tanks, designed to intimidate with impressive technical specifications, failed in the most basic requirement of armored warfare: mechanical reliability sufficient to reach the battlefield and complete the mission. The Kummersdorf testing facility began preparing for evacuation in early 1945 as Soviet forces advanced toward Berlin. Engineers hurriedly packed testing records and shipped technical documents to facilities farther west, hoping to preserve the information for later analysis. Some captured tanks, including at least 2 Shermans, were pressed into emergency service with German combat units defending the approaches to Berlin. These vehicles fought alongside German designs during the final desperate battles of the war, offering one last comparison under real battlefield conditions. The Shermans continued operating until destroyed by enemy fire or abandoned when fuel ran out. German tanks, including Panthers and the few remaining Tigers, broke down from mechanical failure at rates that shocked even experienced crews already accustomed to unreliable equipment. The story of War Daddy II and the dozens of other Shermans tested at Kummersdorf highlights one of the most significant industrial disparities of the Second World War. German engineers working within an industrial system that prioritized theoretical perfection over practical durability produced tanks that looked impressive on paper but struggled in sustained field operations. American engineers, applying decades of automotive manufacturing experience to military requirements, built tanks that lacked some technical sophistication yet functioned reliably under conditions that defeated German machines. In armored warfare, as in most forms of combat, the weapon that works when needed is more valuable than the weapon that is theoretically superior but cannot reliably reach the battlefield. Post-war analysis conducted by American and British intelligence organizations confirmed what German testing at Kummersdorf had already revealed. Examinations of destroyed German tanks showed that mechanical failure was often as common a cause of loss as enemy fire. Investigators found final drives broken by stress, transmissions seized from inadequate lubrication or operator error, and engines burned out from overheating or oil starvation. Germany's obsession with individual vehicle superiority and impressive technical specifications had blinded designers to the critical importance of reliability and maintainability. German tanks required extensive specialized training to maintain. Their engines demanded constant attention from skilled technicians, and their logistics system struggled to supply the countless unique parts required by scattered units. The lessons learned at Kummersdorf directly influenced German armored vehicle design in the post-war Bundeswehr of West Germany. When the Federal Republic began developing the Leopard 1 main battle tank during the 1950s, designers deliberately emphasized reliability and maintainability rather than pursuing extreme performance specifications. They studied American automotive engineering methods and intentionally applied similar principles to military vehicle development. The resulting Leopard 1 incorporated many of the design philosophies that had made the Sherman effective: a robust powertrain with generous safety margins, easy maintenance requiring minimal specialized tools, standardized components that allowed rapid field repairs, and sufficient design flexibility to permit upgrades without completely redesigning the vehicle. The Leopard 1 became one of the most successful tank designs of the Cold War era, serving in numerous armies and remaining in production for decades. The captured Shermans at Kummersdorf, including War Daddy II with its distinctive name still painted on the hull, represented far more than enemy machines brought back for technical study. They were proof that industrial maturity and practical engineering experience mattered more than theoretical technological innovation pursued without regard to manufacturing reality. German tank designers pursued increasingly advanced specifications because they believed superior technology could compensate for material shortages and numerical inferiority. They were mistaken. American tank designers focused on reliability because they understood, through hard industrial experience, that logistics, maintenance capability, and sustained operational availability ultimately determine victory in modern mechanized warfare. They were correct, and their approach proved decisive. The reliability gap between the Sherman and German tanks influenced not only the outcome of the war, but also the direction of armored vehicle design for decades afterward. The reliability gap between Sherman and German tanks influenced not only tactical armored warfare, but also shaped the broader understanding of military industrial capacity and its decisive role in modern conflict. Germany entered World War II with significant technical advantages in many weapon systems. Its scientists and engineers possessed knowledge and expertise that often exceeded those of its opponents. However, Germany lacked the industrial depth and manufacturing scale required to sustain those advantages through mass production while fighting multiple enemies across several fronts. The United States, by contrast, entered the war with weapons that were sometimes less technically sophisticated. What America possessed instead was overwhelming industrial capacity, allowing it to manufacture enormous quantities of equipment while steadily improving quality, reliability, and performance through feedback from combat operations. This industrial approach, perfectly demonstrated by the design and production of the Sherman tank, proved far more effective than German technical sophistication applied to limited production. The United States produced nearly as many Shermans as Germany produced tanks of all types combined. At the same time, American factories built massive quantities of aircraft, ships, artillery, trucks, and ammunition while also supplying Allied nations through the Lend-Lease program. Despite this enormous wartime production effort, the United States still maintained the highest standard of living among all major combatant nations. Germany, even before the effects of Allied strategic bombing intensified, could never match this economic output. In the end, industrial mathematics proved as decisive as any battlefield victory. The logic was brutally simple. A Sherman equipped with a 75mm gun that reliably reached the battlefield and fought effectively was far more valuable than a Panther with a superior gun that broke down before engaging the enemy, or required 3 days of maintenance for every day of operation. A tank battalion with 80% of its vehicles operational could carry out missions that a battalion with 40% readiness could not even attempt. Reliability was not merely a convenience or secondary feature. It was the foundation of operational effectiveness, determining whether armored forces could perform their assigned missions. German tanks repeatedly failed this fundamental test throughout the war. American tanks consistently passed it. Testing at Kummersdorf had already proven this beyond reasonable doubt by mid-1943, even as German commanders continued deploying Panthers and Tigers that appeared formidable on paper but could not always be relied upon to function when needed most. The Sherman tank did not win World War II through superior armor or overwhelming firepower. It won through industrial superiority expressed as reliability, availability, and ease of maintenance. German engineers at Kummersdorf understood this reality by mid-1943 through their exhaustive testing programs. They wrote detailed reports documenting their findings. They repeated their experiments with scientific rigor and reached accurate conclusions about American industrial advantages. But understanding a problem and solving it are two very different challenges. German industry lacked the ability to reorganize production around reliability principles while simultaneously fighting a losing war across multiple fronts against enemies with far greater resources. American industry had already built reliability into its civilian automobile sector through decades of competition. Those mature engineering and manufacturing practices were simply adapted to military production, with remarkable success. War Daddy II, the single Sherman tank captured in Tunisia and tested for months at Kummersdorf, quietly demonstrated this reality. Every kilometer it traveled without mechanical failure showed that German tank design had chosen the wrong priorities by emphasizing technical specifications over reliability. Every test confirming American automotive engineering excellence revealed the importance of industrial maturity and practical manufacturing experience. Every comparison between Sherman and German tank reliability demonstrated that American engineers had solved problems German engineers did not yet fully recognize. The tank itself was not extraordinary. It was simply one of more than 49,000 Shermans produced during the war. But what it represented was deeply unsettling to German confidence. It was proof that Germany had already lost the industrial war, even while the fighting continued, and that American production capacity could not be matched regardless of German technical sophistication or battlefield skill.